Hi, this is the fifth video of the series of videos that I'm going to explain about quantum computing. In this video, I'm going to talk about Deutsch-Jozsa algorithm, which is a slight generalization of Deutsch's algorithm we observed in the previous video. So what is Deutsch-Jozsa algorithm? So in order to explain about this, we need to talk about the function in n bits. Let's talk about a function that sends n bit strings to 0 or 1. We call this function balanced if the number of inputs whose values equals to 0 is the same as the number of inputs whose value is equals to 1. And we call the function constant if the value of function is always 0 or 1. So balanced and constant is not all the types of function. However, suppose that you are given with a function. We don't know what that is, but all we know is that the function is either balanced or constant. So the question is, how many times do we have to query this function in classical algorithm to find out which type this function is? So if you're lucky and you query this function twice and you find one case you get the value of 0 and another case you get the value of 1, then you immediately conclude that this function must be balanced. However, you could be unlucky that you query the function always gets 0, so you have to keep query the function until you get 1. But how many times do we need to query in the worst case scenario? We need at least the half of entire number of inputs, which is 2 to the n. So when n grows, the number of queries grows exponentially. So it means that the algorithm slows down. However, the Deutsch-Jozsa algorithm can find the type of a function in a single query. This is how the Deutsch-Jozsa algorithm look like. So the bottom wire is the output wire, and the top wire is the input register, which consists of n qubits. That our oracle, which represented as a symbol F. So in this case, the input register consists of n qubits, so I put the n subscript here. So you can see this is almost similar to Deutsch algorithm. And what happens at the end is you measure all these input registers. So you need to measure n times. Now, before we going over the actual quantum state, we need to understand the operations of Hadamard gate. So when your x is either 1 or 0, when you act on Hadamard gate, then you can write that out as the following. It depends on whether x is 0 or 1, only changes the sign of ket 1. So you can change the sign of ket 1 as this expression. And also, we're going to denote the Hadamard gate acting on n qubit state, each of n qubit state as the power of tensor n. So when I have this, so 0n means that there are n zeros in the list, means that I apply the Hadamard gate on every 0 cats on n qubit state. And what happens is, it gives me the linear combination of all possible quantum state. Having this, let's begin our computation. So I'm going to separate each cases as 0 to 3. At 0, we initialized as 0 and 1. And in the first state, you just applied Hadamard gate. So as I said, when you apply the Hadamard gate here, it's summation of all possible state. And then you apply the oracle. So I don't know what the function is, but 0 plus fx is just f of x. 1 plus f of x is the opposite of f of x, denoted as het f of x. So and then I can rewrite this as the following. So it's either 0, 1 or 1, 0. So only changes the sign depending on what x is. So it took out the sign with the minus 1 to the f of x, and then just write it as Hadamard 1. So and then let's compute another one. So we applied Hadamard again to the input registers. So when I have the function which is constant, then you can see that my sign is always the same. So I can just get rid of the sign. And then this quantum state, which comes from the first Hadamard in our algorithm, there is a twice of Hadamard gate on every single input register. So when you apply Hadamard gates twice, it's the identical gate. It reverts back to the original state. So you get 0. So what happens? What does that mean? So if f were constant in the beginning, then eventually your quantum state after applying this algorithm becomes 0 in the input register. So you will always observe this 0, 0, 0, 0 if the function is constant, and more importantly, only if the function is constant. So let's say we run through this quantum algorithm and measured all the input register. You always observe 0. Then you can conclude that function is constant. However, if you observed at least 1 in the measurement, then you immediately have to conclude that this function is balanced. So in this video, we walk through the brief introduction to Deutsch-Jozsa algorithm, and in the next video I'm going to introduce another quantum algorithm which is called Bernstein-Vazirani algorithm. Thank you.